I'd like to let you know that you are able to check out a telescope from the library for free. And to do that, you'll just go to the website, you'll watch a short informational video, and then take a quick quiz, and you'll enter your library card number, and that lets us know that you've completed it, and that you're cleared to check out a telescope. And at the end of the program here, I also have a bunch of materials and some handouts that you're welcome to check out any of this today. You can check out the telescope if you've already taken the quiz. So I've got some movies and DVDs and books, and I got a few challenge items there. Don't be daunted. They're free to check out, even if you just skim it and then ponder what you see in relation to the vastness of the cosmos. You're going to be much better off. So there you are. We have George Trimble here with us today, and he's going to just express his views on Copernicus.
And as it turns out, celestial geometry will be one of our topics. So that's a particularly apropos book. Thank you so kindly. So this is the Geauga Skywatchers Club, and thank you all for coming. I'll refer to you guys as Skywatchers from here forward. This is brought to you by the Foundation for Geauga Parks. Sue, can you raise your hand for us? Sue Lundstrom is one of our volunteers. Thank you, Sue. We have also support from the Chagrin Valley Astronomical Society, from which I hail, and the public library system, obviously, as well as the Geauga Park system, the Park District. All of these groups got together to make this possible. We also have Jan and Richard Glove here, if you guys could raise your hand. Volunteers helping us out. I'm very appreciative of their help as well. And we have a new volunteer today. Now, Laura, is it Etling Schwanek? Am I saying that right? Thank you so much, our new camera woman, heretofore one of the audience members. And if you would like to help out, let us know. We'll find a spot for you to help as well. So, says Hesiod, 707 centuries before the Common Era in his days, when the Pleiades, daughters of Atlas, are rising, begin the harvest, the plowing when they set. The Pleiades, also known as the Seven Sisters, wonderful old story associated with those stars. They're a beautiful thing to see through a telescope, but what is he talking about here? What are we talking about? What he is saying is that there is a time to plant, a time to sow, a time to reap, right? And he's saying this has something to do with the stars. So it is long now, long since we've been so attached to the sky in our daily lives. There was a time when we would turn to the stars and to the planets and to the sun and the phases of the moon to help us gauge certain things in our lives. And it's no longer quite the same. Here's a panel from an ancient illuminated book called The Book of Hours. It's at the Musée Chantilly, France. Maybe you can see it when you're over in France. And look here. We see farmers harvesting, shearing sheep. Here is a calendar, and here is the crab, telling us something about the time of year. This book was utilized as a means to remind people what they're supposed to be doing at this time of year, kind of like a farmer's almanac from 1460, back when this kind of stuff mattered. I always thought cerulean blue was a beautiful color against that gold. And then another thing, navigation has been always linked strongly to astronomy, and no longer is it so. We used to, up until even 20 years ago or less, the Annapolis Academy would teach new mariners how to use a sextant to find your longitude at sea. They don't teach it anymore. I heard that they're bringing it back, or they did recently, but they left off in favor of GPS recently. And you've heard about how ships are crashing, these big, ships are crashing in the sea like big Navy vessels. But it used to be very important to know which stars rise just before the sun, which constellations rise. These constellations tell us what season it is. Is this the foul weather season? Is it safe to go out and sea and fish, for example, or to navigate to foreign lands? This is a painting, The Storm on the Sea of Galilee by Rembrandt, one of my favorite artists. So long has it been since we, as a species, lay on the grass at night as the embers of the fire glow red, and listen to an elder point at the stars and tell the stories of the bear. That we are separated from the sky. What do we got going on here? Sorry, I don't know what I've done here. Can I fix this real quick? Did that do anything? That's better. I'm sorry. I keep in a way that our ancestors were not. Increasingly, technology is taking the sky away from us. Tonight, I'd like to bring that back a little bit. Okay. So, these days, nighttime is a time when street lights come on, building lights come on, and the faint beauty, the delicate lacework of stars is washed out. People retreat from the darkness of their homes and turn on an incandescent light or a fluorescent light. And then turn on the telly for the entertainment that was once provided by a cast of characters in the sky and the stories surrounding them. Ancient gods and goddesses and wars and kidnappings, all kinds of interesting stuff. It's just as good as any soap opera today. There's many people who, if you were to ask them, what's the current phase of the moon? Couldn't tell you. I'm not saying that's a bad thing. It's just that our daily lives are done inside for the most part as opposed to outside. And when we go home, we drive in a car, there's a roof on the car. And we go inside and we tuck ourselves in and we just don't look up. And yet, the phase of the moon is once very important. There's not many people that I know, although I know more than most because I'm in an astronomy club, that can point to all this myriad of stars and pick out which little dot, which little bright spot represents a planet amongst all the others. And of course, the tides, driven by the moon and the sun. You have to know the tides if you're going to get into safe harbor in the old days, when it mattered. But now it's all done on your GPS for you. But I know as a sailor, I sail, and when I go to these little remote islands in the Pacific, for example, you can't go in some cuts through the barrier reef unless the tide is with you. Otherwise, the rushing water rushing out against you will prevent you from getting in. You'll crash on the reef. So you have to know the tides, but not so much anymore. Not so much anymore. That's not many people that need that information. So, we have developed ways to regulate our lives without reference to the sky, and so, thereby, are separated from the wonders of the sky in a way that the ancients were not. This brings me to ancient. I think it's worth looking at how people used to see the universe, even if it was wrong. We know now that people 2,000 years ago had wrong-headed notions about how the world works. And yet, I'll make this case tonight, it didn't lead them too far astray. They were able to make powerful predictions. They were able to understand the world and didn't go too far wrong. In fact, Ptolemy, I wonder if we have the Almagest here. We do not. This is a good one though. But Ptolemy wrote us a book called the Almagest around 2,000 years ago, and there was no other astronomy book that survived because it was so thorough. It's all anybody thought was necessary. And it's almost all the ancients have to say on astronomy because it was so successful. And it wasn't until Copernicus came along and disrupted this notion of a world at the center, our world, with the sun and the moon going around, that the Almagest fell out of favor. Now, did you know that the sun is in the middle and the earth goes around? It's true. That's the truth. Now don't forget, because I'm going to show you an ancient theory of astronomy where the earth is still and the sun and the moon goes around. Now, if you think about it, it ain't so crazy. Do you feel yourself moving through space right now? You're on a spinning earth going around the sun, and the sun is going through space within the radial arms of our galaxy, and our galaxy is moving as well. I can't remember. I wish I had told myself I was going to look up the final number, but it's hundreds of thousands of miles per hour, and we feel none of it. So, for all the world, it seems as though we are perfectly still. It's not an unreasonable hypothesis. Tonight, let's explore that hypothesis that we are at the middle, even though we're not, right? We're not. The sun is at the middle. But we're going to pretend like we are in the middle. And we're going to explore the consequences of making some observations about the world around us and build a model and see if that model makes predictions. I'm telling you, the predictions that come from this will blow your mind. Powerful, powerful stuff. And that's why it was so hard for Copernicus and Kepler and Newton to tumble the old world system. It's in part why Galileo was put in jail for being right. So, I'll make the case that this worldview, Earth in the middle, the sun going around, and everything else going around the Earth, while wrong, can be informative. So, the title of tonight's talk, Geocentrism, a Springboard to Copernicus. Now, we might have to break this into two parts in order to accomplish everything that can be, to glean everything that comes from this. But by the end, you will be really, really in tune with the world around you and prepared to accept the lessons of Copernicus and Kepler. We're going to view the universe through the eyes of the ancient observers. Let me tell you where we're going, because it's a long path, it's a journey. I'm going to talk to you about the celestial sphere. Let's deduce it. I'm not just going to tell you it's there. Let's deduce it. And I'm going to tell you about one of three motions that the sun has. I'll tell you about the first, the second, and the third motion of the sun. We're going to deduce the size of the Earth. This is how science is done, right? Tell me about the scientific method. What do you know? Yeah. What is it? Do you know? You got to have a hypothesis. You want to answer a question, right?
Yeah.
You form a hypothesis. Yes. You got to do an experiment, right? You got to test your hypothesis. And then if your hypothesis, your idea survives the crucible of scientific inquiry, It may just move on to become a theory, right? You've heard it before. I see it in your face. All right. So let's see if we can come up with experiments that we can actually do. Remember last time I met with you? Who was here when I taught you how to use a straw and a protractor to determine your latitude by sighting the North Star? You remember? Well, that tool is going to come in handy this time. Do you remember? You have a question? You just okay. Yeah, okay. All right. Good. All right. So, the sun's second motion. What in the world about all this motion? We're going to find out. We're going to draw some conclusions from our thoughts, and then we're going to test our conclusions by discovering the sun's third motion, by asking some questions and seeing what a little mathematics applied to our model spits out. Does it make sense? It will. We'll discover what equinoxes are and solstices. Who's heard of equinoxes and solstices? We've all heard of them. I even have to remind myself every once in a while what it means because it's complicated. The geometry is complicated. And I have to brush up every once in a while to really feel like I've got a sense of why these things occur. What does it mean? I hope to help you with that too. Eventually we'll get to determining the moment of a solstice and how that is done mathematically. Although we won't go into a lot of mathematical details, I do like to spice up these talks with just enough math to show the young people that even if you don't have these math skills yet, that math is powerful. Powerful. And it's not just some boring homework problem about, if you got 2 red balls in one sack and 4 blue balls, this stuff can actually answer cool questions that you may have already thought of before you even met me. Okay? Eventually, we'll discover something called the solar anomaly, and we'll find how Hipparchus, a couple of hundred years before the Common Era, before year 0 BC, had already discovered this thing, and he fixed it. He fixed it and gave us a working model of the universe. That's how old this stuff is. And it has to do with the length of seasons. Hint, the length of seasons should be equal, and they're not. And we'll see why they should be equal. And then you'll ask yourself, well, why then aren't the seasons of equal length? Eventually we'll get to precession, a weird topic, very fascinating. And eventually, not on this talk, we'll talk about something called an astrolabe, a 2,000-year-old analog computer that performs trigonometry, predicts the time of day, tells time. There was a book written by an Arab astronomer in the 5th century that listed 1,000 uses for this tool. It is really cool. It's the universe in the palm of your hand with dials and stuff. We'll do that as another talk. But we got to get this stuff first. And then we'll go to modern astronomy eventually, Copernicus and Newton and those types of topics. Okay, let's do this now. In your mind, we are going to go out in the field and lay in the grass next to that campfire burning low. We're going to look into the sky to the south. That's where all the fun stuff is here, towards the south. And we're going to see what our eyes will show us and think with our brains. What is the meaning of that information? And hopefully, I show you that you can knit together things you already knew into a really neat system of organized information that gives you power over the universe around you. Knowledge is power. So let's follow one day. You're watching as the sun rises. All the stars are out. The sun is starting to rise in the east, right? Gets lighter and lighter, and those stars start to disappear and twinkle out of existence as the sun brightens the day. And the last stars to disappear are those in the west. And the sun rises. Now, we know that just because the sun came up, the stars didn't disappear, right? They're still there. It's like in a celestial game of peekaboo. right? They're there. Even my kid, he's 3, he knows that when I hide after saying peekaboo, he knows I'm still there. He gets it. And likewise, the stars are still hiding there. It's just the glare of the sun and the brightening of the sky hide them, but they're still there. And they too continue to rotate. So that the last stars we saw on the horizon in the west, as the sun rises, those last stars dip down and disappear under the earth. Or maybe they just drop into some hole and go down into Hades. There's been all kinds of philosophies about what happens in the west, right? But I want to make the case that we know better if we're careful with the way we think about this. So, what do we see is, we see that the sun starts low in the west, and it rises throughout the day. And this is due south. We're looking south. The North Star is behind us. At the apex of the day, what do we call that moment when the sun is highest? Dead south of us. What time is it? Noon. It's noon. So this is astronomical noon. And I think when we talked about sundials, I told you why astronomical noon doesn't always match up with what's on your clock. The equation, remember that? The equation of time and all that stuff. But at least the world thinks it's noon, if not our watches. Now, the sun then continues down into the other west. You see the sunset turning kind of an orange here. Our first daytime passed. And what do we expect is that the skies will start to darken here first. The stars will start to twinkle into existence. As the sun rotates down, the stars will come out. And they're not just sitting there. They're moving, just like the sun, as if attached to the lining of a giant barrel. Okay? The sky seems to be revolving around us. This is the first motion of the sun, the one that we know. The sun seems to move. Rises in the west, sets in the east. It culminates, it sets, it rises, and the stars do the same, as we'll soon see. Let's look at the west. As the sun has set in the east, the stars rise, and this is a time-lapse photography, or photograph, that has left the stars exposed to the film as they moved, so we see streaks. What do we notice about these paths? What jumps out right away? Does any one path cross? These paths are all parallel. They don't cross. It's as if the stars follow their own track as set down for them, and they do not deviate. And in part, this is why the constellations, those groupings of stars that our brain says, man, that looks like a bear or a dog, they move together. They don't cross. They don't mix up. For thousands of years, these constellations have had a very similar look, almost the same, over time that we appreciate. And then they set together in the west, following the track laid down for just that star. Every night, that star on that track. You see it? Now, let me tell you something. The sun does not follow this same pattern. Each day, the sun will rise on one of these tracks and stay on that track for that day. And on the next day, it will have dropped into another track. The sun is doing its own thing, on its own rhythm. And I ask you why. This is stuff you can see, you can watch. If you watch long enough, you'll notice things like this. And you would, if you're curious, and you are, or you wouldn't be here, you would ask, why? What's going on? Can we sort it all out and make sense of it? And I hope to by the end of tonight's lecture. So as I say, there's this thing, celestial peekaboo going on, right? The sun is hiding the stars from us, and you might think, well, if the sun always rose, with the same stars, we would never see certain stars ever. They would always be washed out. And yet, we have convinced ourselves that we have seen all the patterns of constellations. It's because the sun isn't moving at the same rate as the stars. As its first motion goes by, it's doing something else. And it exposes all of the stars eventually over the course of a year. So we can see the full pattern of stars and constellations come by as the year goes by. Not on a single night. The sun, of course, during the daytime blocks out certain constellations, but throughout the year, if we watch long enough, the order of the constellations becomes apparent. Imagine yourself in a building and you're looking out a window, and there's a circle of kids dancing around the building. You can't see them all at once, but as they circle around, you can start to find the pattern, and you'll be able to identify all the kids in the right order. This is very much like what's going on out there. The sun is creating the window for us. Aries, the ram, the constellation that the ancients thought looked like a ram. One of the important constellations because it is the Greenwich of space. Greenwich. You know, longitude on Earth is marked from Greenwich, England, right? Everything east and west is numbered from that 0 point. And Aries, this constellation, represents the 0 point in space. That's how astronomers define longitude in space, from Aries. The ram always rises before the bull. And after Taurus comes Gemini, then Cancer, then Leo, then Virgo, then after Virgo comes Libra, then Scorpio and Sagittarius, Capricorn, Aquarius, and Pisces. And then, in an endless circle, we get Aries. How many are there? 12. There's one constellation for each division of the year. The sun, it turns out, spends about a month in each division, giving us 12 months. Pretty cool. Now, you probably knew this, but as this starts fitting together, you're going to start seeing how little tidbits of knowledge that you had start to come together in a more accessible way for you, I hope. So here's a hypothesis. The Earth in green sets in the middle of space, motionless. And on the surface of a giant celestial barrel are glued the stars. Now this isn't preposterous. There were some ancient thinkers that really did think of the firmament as a crystalline structure upon which the stars were glued. Like little lights, fires, they thought, perhaps. Or perhaps there was a giant fire that surrounded everything, and this was a black tube in which were poked little holes, and so we were seeing the fire coming through the holes as it turned. That was another theory. And what's wrong with those theories? There's nothing wrong with any hypothesis, but you try to test it. You sort the wheat from the chaff, like those ancient farmers. So here's one hypothesis. Does it make sense? Let me show you another picture. And then you tell me. Now, we're facing south heretofore, but now let's turn around and look north. And there's the North Star. And if you watch the stars around, the North Star all night, all the other stars are moving from east to west, just like the sun does. Around the North Star, there are stars that turn a circle. And the farther away the star is, the bigger the circle it draws. Do you see them? There's the North Star right in the middle. It doesn't move. And so even though something is turning out there, the North Star seems not to move. And at some point, the stars get so far away that they actually set here in the west. And then, there it is. He rises again. And if you go far enough away, these circles turn into lines, like in our previous slides. So now, you ask yourself, well, if I was in a barrel, a celestial barrel, I should see nothing out the end. Shall we look at the previous slide? If we're living on an Earth surrounded by a celestial barrel, and if I look straight up, no stars up there, just black. But that's not the case. That's not what we see. We actually look north and we see stars, and they seem to close on a single point, which leads us to a different hypothesis. Maybe it's not a celestial barrel. What is it? Did somebody say a cone? That's an interesting proposition. Did I hear a sphere? Sphere? Okay. And it happens at the South Pole too. So we wouldn't call it a cone. A cone comes to a point. It could be a cone. I heard somebody say cone. But if it happens at the South Pole too, then we're stuck. We need a better shape. And so we conclude that there's this thing that acts like a giant sphere going around Earth, round and round, carrying the stars, so that the North Star doesn't move as the whole thing turns. See the turning? You turn this pole down here, the Earth sits in the middle, and the stars seem to rise and set, rise and set. Now, because we should give credit to one of the oldest and most venerable of astronomers, Ptolemy, but just to see that this has been thought of for a long time. This isn't new. This is ancient thought that we're recapitulating here. We're redoing what ancient people have thought. But most of all, the observed circular orbit of those stars, which are always visible, and their revolution about one and the same center, led them to this spherical notion. For necessarily, this point became the pole of the heavenly sphere, and the stars nearer to it were those that spun around in smaller circles, and those farther away made greater circles in their revolutions in proportion to the distance. Now, having seen what you just saw on previous slides, the words of Ptolemy echoing down the halls from 2,000 years ago make perfect sense. And he goes on to say, there is no other hypothesis that works. And so we may take for a given that the shape to be concerned with is a sphere. He was wrong, but it seems so right. Doesn't it? All right. Now, let's consider how big is the Earth better. Because we know it's kind of big. I can't hardly walk from here home. I live in Van Wert, which is 3.5 hours away, and it's pretty big. I'm not walking home tonight, and I know that isn't as far as some people live from here. So I have a sense that the Earth is big, but the better question is, how big is the Earth compared to the rest of space? Is space small? Like you could shoot a bullet up and hit the sun? Or a star? Believe it or not, there was a time when people thought that it was just out of reach, that those stars were close. So is there an experiment we can do to discover just how big or small we are in comparison to the solar system? Now, who was at the very first talk we gave? The folded activity where we folded paper and folded, and this is the solar system, the paper, and that little last fold was the distance from the sun to the Earth. Do you remember that? We already know that the Earth is small compared to the rest of the universe, but that was just the solar system. Let's contemplate stars. That's the Earth. You noticed it changed color from the last slide. And let's pick two stars and put them circling the Earth on that big sphere that we talked about last time, on the last slide, right? You see those two stars? Now let's have a guy close to the North Pole take an angular measurement on those two stars with a protractor, very much like we built last time. Did you measure your latitude with the... Did you go home and do the experiment? Yeah. Good. So this guy measures that angle with a protractor and he comes up with 39 degrees. And the question is, what would I measure if I was near the equator? So he goes down there. It's a long walk. And he measures 44 degrees. Oh, interesting. Now, the measurement, if he could go to the center of the Earth, the measurement that separates those two stars is actually 34.8 degrees. Now, this is what happens if the size of the Earth is big compared to the size of the universe. If the universe is small and the stars are close, there should be this parallax effect, this differing angle measurement thing going on when you move around the Earth. Your point of view matters if things are small, if the stars are close. Let's do the experiment again, but let's take this circle out to about here and put these stars out on that circle. I almost pulled my computer off here. Now, I made the circle so big it wouldn't fit on the screen, so I zoomed out. You guys follow? I zoomed out. Look how small the Earth got. We're farther out in space looking down now. Okay? Now what happens when a guy at the North Pole and a guy at the equator take those same measurements? The green measures 35. The guy with the black lines here measures 35. And of course, the central angle remains the same, 34.8. What we see is these measurements are converging on each other, and they're converging on the true central measurement. Now, if the world is set up like this, we should be able to do this experiment. And the results of this experiment will tell us if the universe is big or small. In fact, if we make this really big, there would be no difference between any of these numbers. The farther out that circle gets, the less the difference is until it's unmeasurable. Anybody have an idea of which of these two experiments was borne out? It's really one experiment. Which result did we find? It turns out that this is it. Next time you're in New York, pick two stars, take an angular measurement between them with a sextant or calipers or a protractor with a straw and a weight, like we did last time, and compare it to the next time when you're on the same two stars when you're in Florida. There is no difference. Zero. Even with the finest instruments, we cannot detect this difference, which means it implies that the Earth is as a point to the universe at large. We are nothing but a ditzel of a dot of a hint of a hair. Nothing. The universe is enormous. The stars are very far away. That's what this experiment tells us. Now, you might think, I discovered something interesting here. But yet again, Ptolemy has beat me to the punch 2,000 years ago and before him. And keep in mind, in that last slide when we read about that the size of the Earth, or no, what was the last slide when I quoted Ptolemy? The sphere, yeah. He was saying that the ancient people, he said the ancient people had figured this out. So he was talking about people more ancient than him. So these are old ideas. A strong indication of this is the fact that the sizes and distances of the stars at any given time appear equal and the same from all parts of the Earth everywhere, as observations of the same objects from different latitudes are found to have not the least discrepancy from each other. So, again, we are recapitulating the efforts of ancient people here, trying to find out a little something about the world around us. And in fact, if this is true, who was at the sundial lecture? Sundials couldn't work if this were not true. Sundials would not work. Remember we talked about the idea that stars are so far away that the rays that hit the Earth from each star are parallel by the time they get to us. Remember? Okay. You remember, don't you? You were there. All right. You've seen this before in one of my previous lectures when we talked about Carl Sagan. Pale blue dot. Remember? This little dot right here, looking back, this is Voyager, going away into deep space, has passed Saturn. It's looking back and it sees Earth. And as you can see, we are insignificant in size. And this is only our neighborhood, the planets. This is just our neighborhood. Okay. So, I think we did this before, the shape of the Earth. So I'll run through it quickly. What is the shape of the Earth? For all appearances, it's flat. Locally, you look out at the horizon, it seems flat. When you stand at the edge of Lake Erie and look out, the water seems flat. It was very hard to convince at one time that the Earth was round. And yet we knew it a long time ago. Columbus did not think he was going to sail off the edge of the Earth. Sunrise seen instantaneously at all points on Earth. Everybody at once would experience sunrise, and yet that's not what we experience. If the Earth was shaped like a bowl, the West would see the sunrise before the East. It's opposite. It couldn't be that shape, right? It seems crazy. But by using our eyes and a little reasoning, we can come up with the truth. This guy sees the sun at 90 degrees from him, just sees sunrise, and this guy's still in the dark. The Earth is blocking him. He's to the west. And here, the sun's at noon for that same guy, coming straight down. Well, now he's now just experiencing sunrise. Strong evidence that the Earth is at least got a curvature this way. Perhaps it's a big barrel like this, like a tube. Like a Swiss roll. Delicious. Here's another bit of evidence that Ptolemy came up with, and this was old when he quoted it, but have you ever noticed that ships, as they sail away, don't just get smaller and smaller, but they also seem to sink down? The last thing you see is the top of the sail, because the Earth is blocking the view. And the list goes on, and it turns out that no matter which way you look, this effect is in place. So if we were on a Swiss roll, there's a flat, long edge where this wouldn't occur. But because it curves in all directions away from us, this effect proves to us that we're on a sphere. And so Ptolemy says that the Earth is sensibly spherical. Okay. Why do we need this? We're building with blocks. We're finding Legos. And pretty soon, from these Legos, we are going to build a superstructure. Something complex and beautiful. I'll admit, some of this stuff, one little Lego at a time, but it starts getting more exciting as we put them together, okay? Let's do a thought experiment. Again, I'm facing south. It's noon because the sun is dead south. It's at the highest point for the day, okay? It rose, it came up to here, and it's at this moment that we're interested in doing this experiment. Now, this is a thought experiment. The sun is too bright to simultaneously see the sun and a star in the sky at the same moment. But let's imagine if the sun were dim, hazy, dim, so dim that the stars popped out and we could see both the sun and the stars at the same time. Imagine a moment when both some star and the sun were on the southern meridian, that's our line, north-south line, at the same time. Now I ask you to do this. Get your stopwatch ready. Okay? You're going to close your eyes. And we're going to set our stopwatch. And we're going to open our eyes 20 hours, 56 minutes, and 4 seconds later. I say open, and you hit your stopwatch, and you read 23 hours, 56 minutes, and 4 seconds have elapsed. What do you expect to see? You can expect, that's almost a day, first off, right? It's almost 24 hours. We can expect that the sun will have set All of night went by, the sun rose, and now it should be pretty close to back where it was. Okay? So you open your eyes and boom, it looks like the sun just rose. What happened? Now I told you the sun has this daily motion, this first motion. It goes around west to east. Now we've just discovered something interesting. The star is right back 23 hours ago, 56 minutes and 4 seconds ago, but the sun is late. The fact that the stars came all the way around defines what's called a star day, a sidereal day. A solar day takes a little longer. The sun needs an additional 3 minutes and 56 seconds to return to the meridian. Now let's see. That's right. So we have to wait an additional 3 minutes. The star will have moved a little and then the sun will be back where it was the day before. What's going on? It turns out that the sun is late. It's riding the it's riding the train, the celestial sphere with the stars, but it's not glued to the surface. It's rolling along a little bit slower. It's like the guy, now imagine if you're at the airport and you're watching people go by waiting for your plane, okay? You know those people movers, the escalator, what do you call them? People movers, thank you. Yeah, people movers. There's people that are on the people mover and they're moving, without walking, they're moving to the right, your left, okay? But there's this one smart aleck. He's a kid, he's being funny, his parents are real irritated with him, but he's walking backwards, right? He's still going forwards, but he looks like he's going forwards slower than the rest of the people because he's walking backwards. So he is making progress to this side, but at a slower rate than the rest because he's walking backwards. This is what is going on here. The sun is going a little slower. It's carried around by the celestial sphere, but it's falling behind because it's got the brakes on a little bit. And it turns out that it falls back about 1 degree per day. 1 degree per day. Now, how many degrees in a circle? Yeah. Now, it's not exactly a degree a day, but how many days in a year? 365. And I'll be pedantic, and a quarter. And that's important because we just had leap year. February this month, this just past February, had 29 days instead of 28. And it's because for 4 years we've been losing that quarter of a day. So that's why an astronomy geek says, don't forget about that quarter a day. But, so it's slipping back by about a degree a day, so that it takes 360 degrees, it's falling back through that whole 360 degrees over 365 and a quarter days. That's the definition of a year. It's when the sun will finally, remember that previous star I showed you? The sun will keep slipping behind. Each day when you close your eyes, open, close your eyes, open. The star is always there, right on time. Tick, tock, tick, tock. The sun is farther and farther by a degree a day. The definition of a solar or tropical year is when the sun is all the way back, so now it's in front of the star, and finally they've come back and meet. That's a year. Okay. There's my, next slide. There's my people mover. All right. So, let's be a little more formal about this thing that we just discovered. This is really, really interesting. Let's do like the ancient Egyptians and Babylonians and look to the west, just before sunrise. And let's look at which constellations are rising just before the sun breaks and washes everything away so you can't see it. We ask ourselves, right before the sun rises, which stars are on the horizon? And here we see Pisces, constellation Pisces. I've given it its little astronomical symbol because I'm not going to sit there and draw every spot within the constellation. But that represents Pisces, 2 fish. We call this a heliacal rising. A heliacal rising, sun. Right before the sun, what is rising? Pisces is what is there. Now this is the picture 2,000 years ago. It's not quite like this now, and I won't explain now why, but just keep it in the back of your mind. The observer is at the equator, so when he looks east, it looks like everything's coming straight up and over his head, okay? And you see that the paths that the sun or the celestial objects will take are marked, okay? This happens to be at what we call the vernal equinox. That's when days equal nights, and I'll explain this better soon. Now, let's wait a month and see what happens. Not that. Now let's look again a month later. Now Pisces has risen, but where's the sun? It's late. Now we have Aries rising, and then finally the sun rises after Aries. And the observer says, last month the sun must have been in the constellation of Aries. It was in front of those stars because it rose at the same time as the year. You see? And a month later, Taurus rises before the sun. And the observer says, last month the sun must have been in Taurus. It seems to be slipping back with respect to the stars by 1 constellation a month. 12 constellations, 12 months, 1 year. Right? Now I am certain, says this observer, that the sun is arriving later every month. It seems to fall back 30 degrees. Okay, what's 360 divided by 30? 12, yes. Sorry to put you on the spot. I know I would have not been able to do that one in my head. Calculus, fine, not adding and subtracting. So that's about a degree a day, as we already discovered. And so he makes the conclusion that since Gemini is now rising, that last month, when Taurus was the one popping up just before the sun must have been in Gemini, the constellation of Gemini. And now he says Cancer must have been last month, and I now predict that the sun is in Leo. So right under the sun right now must be Leo. Let's see what happens next month. Was he right? There's Leo. You see the sun keeps falling, slipping back later and later. New stars are rising before the sun. And it's for this reason, remember the peekaboo? It's for this reason, this is the window I was talking about. The sun is allowing us to see stars that were heretofore covered up by its light because it's slipping back on the people mover of the sky. Okay? So let's keep going. Pisces. Again, back to Pisces. We've completed this cycle. And you see that the sun keeps slipping back. But who notices something else? What do we call that? Anybody? From trigonometry. What kind of wave is that? Yes, it's like a sine wave. You see it? There's a wave going on here. And a child shall lead us. So, you see that the sun not only is falling behind, but it's oscillating back and forth throughout the seasons. Do you see it? It started here, it traveled this way, and then back, and then back. That's interesting. And ancient cultures knew this. Why? Because they noticed that there's a mountain on the horizon, and in winter, the sun rises on that side of the mountain, and then at the solstice, the sun rises right off the tip, and then later in the year, the sun rises to that side, and it goes back and forth between very well-defined limits, which we will discover. So, we've discovered not just 2 motions of the sun, a daily motion, a falling back motion, and now a wagging back and forth sine wave motion. Very good observation. So let's run through those again. I want you to see. Here it comes. Ready? See it moving side to side on the horizon? That's the point. Oh, I'm sorry. I got myself in trouble. This point, if you were to put a stone on the horizon and use that as a reference marker, you would see the sun rising from a different spot in the east and setting in the same way on the other side at night. What does it all mean? Give me some closure here. I'm getting there. This is all coming together. So we've discovered the second motion, and it takes a year for the sun to cycle through that second motion, which gives us the length of the year. And we just had a hint at that third motion about which I spoke. So we have the sun revolves around the earth daily from east to west. It falls back from west to east over a year, and it seems to wander. Now I say up and down here, side to side if you're looking at the horizon, but at noon, because it rose further to this side, it seems higher, and then at other times it seems lower. So when you look south, the sun is either higher or lower at noon, and it vacillates up and down, up and down. When the sun is real low in the sky at noon, what season are we in? Yeah, the cold season, winter. The season where the ancient people would worry, is the sun going to keep getting lower and lower and lower and maybe just disappear? Maybe it's endless cold, and there's all these wonderful stories that ancient cultures had about, and practices, about strengthening the sun. Maybe you have to do a special dance or sacrifice someone in the tribe to get their blood strengthens the sun, right? These are actual practices, actual beliefs, and actual fears. How would you like to be living in a cave and it's getting cold and the sun's getting lower every day and you wonder, will it ever come back? And do I have any power? And if the shaman rattles his shaker just right, oh, guess what? It's coming back. That shaman, man, that's some powerful stuff. Okay. Golly, the time flies. Okay. So here in gray are the constant, this is the whole sky mapped out, and we're going to discover what this means. This is declination, that's the height, and this is the side-to-side part. Remember I said Aries is the starting point, like longitude in the sky. And so different constellations are located at certain height and certain distances over from Aries, and we can map things out. And I'll show you how we're going to discover this map. But just as a hint, the ones noted in gray are those constellations through which the sun travels throughout the year. The sun at a certain time of year is in Leo, and so we can't see Leo. And do you see your sine wave, dear? You see the sun, the little dots? Each of these represents a day. The sun fell back a degree. It's falling through Pisces. It's entering Aries. And it creates this sine wave pattern if we unroll this map. And there again, we discover this strange sine wave. Now, the next topic is to figure out how can we place all the stars in their respective locations on the map. How can we put them at the right height or above or below the equator here at 0, okay? How do we place them in the proper right to left orientation? And how do we map the sun onto all of this? And then we discover that when we roll it up, the sine wave disappears and it becomes a disk, which is the disk of the ecliptic, which is angled with respect to our equator. And now we're building some cool castles out of these Legos. This next talk gets really cool. And unfortunately, this is as far as we're going to be able to get in this lecture. What we have discovered to this point is this third motion of the sun. That's all there are, just 3. This oscillatory motion, side to side. And the extremes, it turns out, mark the moments of the depths of winter, when it's as far south of us rising on, we're facing west, and when it's as far south when it rises, that's the lowest it's going to get. It turns out 23 degrees from the equator. 23.4. That's going to be winter, the depths of winter. That's when we celebrate rebirth and hoping that the sun is going to come back alive. Think of the evergreen tree, an ancient tradition that predates Christianity. Okay. When the sun is the furthest north is summer. And then the points where it crosses right in the middle are the equinoxes. Now, what do those mean? And what can we do with them? It turns out we can start to produce this really powerful model. We can plug some data into it, and it starts spitting out things like, let me put it this way, modern orbital theory based on modern physics spits out things we call orbital parameters, like the eccentricity of the ellipse, like how close is the sun to Earth when the Earth is at its closest approach to the sun. We know in reality that the Earth is going around the sun in an ellipse. So one end of that ellipse is closer to the sun than the other end. And it influences our seasons and our climate. And we've got this thing called axial tilt. And all of this influences weather. It turns out that we can predict how elliptical our orbit is only using Ptolemy's model. Start spitting out like the apsis paradox and apapsis. These are the farthest points the sun is and the closest point. It spits out the moment of the equinoxes. This model starts spitting out all kinds of numbers, and you can go check them on Wikipedia. And these are modern orbital theory parameters. Now, we don't have to do a lot of complex math. I don't want to scare you away. A simple drawing will suffice, and you'll go, whoa! So what we'll have the kids do it next time. I'll hand you the calculator, and I'll say, here's a length of a line, and here's a length of a line. Divide them. Boom. You've got the eccentricity of the orbit. Just from a drawing we did with these assumptions. And then we can look them up on Wikipedia. I'll ask you to go look up the argument of aphelion. It'll be right there. Same number, exactly, to 3 decimal places. Questions? Come on. What's the meaning of life? Mm-hmm. There is, in truth. Your question is, why don't we talk about the motion of the Earth? Because I don't feel it, and I don't see it. And I'm putting myself into the mind of a 2,000-year-old guy just looking out in the field, up at the sky. So I'm not going to assume that I have a modern textbook that tells me that the sun is the center and that this is an ellipse and the sun is at a focus. I'm not going to pretend any of that. I'm just going to take the simple assumptions that I can see and feel and see how far we can get. And then I'll show you eventually how it breaks down and why Copernicus enters. And then we have to accept a solar-centric model, and then we see how the Earth moves and what is axial tilt and what happens with precession and all these other complex ideas. But our minds will be better prepared if we keep it simple and then move to complexity. We can add on icing on the cake as we go. And get a little historical perspective along the way, an appreciation of the hard-bought science, centuries upon centuries. Ptolemy relied on to prove his theories, and we build on those giants ourselves. So I don't talk about the Earth's motion just yet, but we will get there in this group.
But I can tell you it's 67,000 miles per hour.
Hey, thank you. So we are moving at 67,000 miles. Thank you so much. That was killing me. I wanted to have that little tidbit of trivia for you. That's great. Do you feel like you're going 67,000 miles an hour right now? That's the difference between acceleration and velocity, and we'll talk about that when we talk about special relativity. You can't perceive unaccelerated motion. Obviously, we're moving 67,000 miles an hour right now through space. Okay, any questions? Yes, Lee.
The nature that measures the diameter of the Earth at 2 points. Can you explain how you did that?
Yeah, that guy was named Eratosthenes. He noticed that on a certain day of the year, the sun was directly overhead, so perfectly overhead, in fact, that he could see the reflection of the sun at the bottom of a well in Seen, near Alexandria, about 500 units away from Alexandria, north. He correctly hypothesized that since he could see the unobstructed full disk of the sun all the way down the well, it must be straight up over that point. Using that information and some trigonometry, I've got a whole, maybe that'll be another talk. I've got a whole lecture on this. He was able to calculate with nothing more than simple trigonometry the circumference of the Earth. And you know what? Had Columbus relied on his estimate instead of someone else's estimate when he left Spain, looking for the Indies, he would have known he wasn't in the Indies by far. He relied on a bad later estimate. He would have been better to rely on the more ancient estimate. Astronomy is cool stuff. Over coffee one day I'll show you exactly. It's a little too complicated to answer in a few minutes, but that's the idea. Just simple trigonometry, the length of a shadow. All right. Yes, sir.
We're very lucky to live in Ohio because in Ohio there are Indian mounds that are more ancient than the Indian tribes. They were individual families then that they built over many generations. Mounds.
Yeah.
And the mounds have mark the astronomical points when things rise on the horizon.
Yeah.
And they've studied them and they've discovered that they're more accurately marked or positioned than either Stonehenge or the pyramids and it's a fascinating thing that right in our state there's evidence of
it's true.
Observed observation.
The serpent mounds.
The serpent mound is one of them.
And you're right. These predate Indians like the Cherokee and the Arapaho. These are Paleo Indians, archaic Indians. It goes to prove that what brought you here today is something deep in the human psyche. It's been driving people for millennia. The quest for understanding. Those folks were taking measurements and observing and trying to sort it all out. There are burial mounds with orientations. I've got another lecture that I'm going to give for this as well about ancient astronomical alignments like Stonehenge. This is the same curiosity that we share here tonight that links us to the ancient past. Yeah, thanks for bringing that up. We are lucky. Yeah.
I haven't seen them yet, but I want to go see them.
Well, now we all got to it. We can do a field trip. Well, make sure you check out a book, and maybe somebody check out a telescope. Yes. Thank you as well. Thank you. We're not done. Come back for part 2.